JMB, how are you all? I hope you all are great. Welcome back to my YouTube channel. My name is Ranpara. I'm a PhD scholar in the Department of Chemical Engineering at the Indian Institute of the Technology, ROPA. So in today's lecture, we are going to conclude the industrial numerical example which follows second order reaction kinetics, right? So let's get started. So in today's lecture, we are going to understand the engineering conclusions where we have kept all the operating parameters to be constant. We have used different reactor models. The different reactor models like CSTR, PFR, batch, and packed reactor, and the reaction follows second order reaction kinetics with the given rate law minus RE is equal to KCA square. Now, we were trying to analyze how large volume of reactors do we require in order to achieve the reaction conversion of 90%. We were trying to analyze what will be the reaction time in order to achieve the reaction conversion of 90%. We were trying to calculate how much amount of weight of catalyst do we require in order to achieve the desired conversion of 90%, right? So we'll understand the engineering conclusion, okay, by using different reactor models, right? So let's get started and let's understand. The first reactor model which I have selected is CSTR, continuous stirring reactor model. So in order to design the volume of the CSTR, right, let's say we are keeping all the operating parameters to be constant and the reaction is carried out in the CSTR. The reaction follows second order reaction kinetics with the given rate law minus RE is equal to KCA square. In order to design the volume of the CSTR, we have used the fundamental concept of the performance equation of CSTR, right? So by using the fundamental concept of the performance equation of CSTR, we can calculate the volume of the CSTR required in order to achieve the desired conversion of 90%, right? So by using the performance equation of CSTR, we have calculated the volume of the CSTR required, which comes out to be 13.5 cubic decimeter volume is required in order to achieve the desired conversion of 90%. Now by using the fundamental concept of the space-time, where the space-time is the ratio of volume by its volumetric flow rate, right? So by using the fundamental concept of the space-time, we have calculated the reaction time, okay, the time required in order to achieve the 90% conversion, right, which comes out to be 0.9 hours. Okay, so which means if we use CSTR as the reactor model where we have kept all the operating parameters to be constant, the reaction is carried out in the CSTR reaction environment and the reaction follows second order reaction kinetics with the given rate law minus RE is equal to KCA square, right? So in order to achieve the desired conversion of 90%, we required 13.5 cubic decimeter volume of the CSTR and 0.9 hours of reaction time in order to achieve the desired conversion of 90%, right? I hope you understood. So the reaction follows second order reaction kinetics, right, where we have the given rate law as minus RE is equal to KCA square, where the reaction rate is indirectly proportional to the rate constant K and the concentration C square, right? Here we have remember that here we have used the second form of CA, which represent the fundamental relationship and also defines the conversion, right? So CA is equal to CA naught into 1 minus XA. We have used the fundamental concept of the space-time. The space-time is the ratio of volume by its volumetric flow rate, by which we can calculate the time required in order to achieve the desired conversion. Okay. Now, we have also used the fundamental concept of the bulk density, where the bulk density is the ratio of weight of the catalyst required divided by the total volume of the total volume occupied by the solid catalyst, right? Okay, I hope you understood. Now the second reactor model which we have used is PFR, plug flow reactor. Now by using the plug flow reactor, remember that again we have kept all the operating parameters to be constant. Now the reaction is carried out in the plug flow reactor. The reaction follows second order reaction kinetics with the given rate law minus RE is equal to KCA square. Now in order to design the volume of the plug flow reactor, recall we have understand the fundamental concept of the performance equation, right? So by using the fundamental concept of the performance equation of PFR, we can design how much volume of PFR will be required in order to achieve the desired conversion, right? So by using the fundamental concept of the PFR, by using the fundamental concept of the performance equation of plug flow reactor, we have calculated the required volume in order to achieve the desired conversion, right, which comes out to be 1.35 cubic decimeter volume. of the plug flow reactor is required in order to achieve the desired conversion of 90%, right? I hope you understood. Now again, by using the fundamental concept of the space-time, we have calculated the reaction time required, okay, which comes out to be 0.09 hours, right? Which means 5.4 minutes of reaction time is required in order to achieve the desired conversion of 90%, right? Which means by keeping all the operating parameters to be constant, if we carry out the reaction in the plug flow reactor and the reaction follows second order reaction kinetics, where with the given rate law minus RA is equal to KCS square. If we use the PFR as a reactor, then we required 1.35 cubic decimeter volume of the PFR and 0.09 hours or 5.4 minutes of reaction time in order to achieve the desired conversion of 90%, right? I hope you understood. Now let's say, what if instead of CSTR and PFR, what if I use batch reactor? Then how large volume of batch reactor do we require? What will be the reaction time, okay, in order to achieve the desired conversion, right? So let's understand that. So in the previous lectures we have calculated we have understood the actual method to design the volume of the batch reactors, right? Okay, so by using the recall, by understanding and by using the performance equation of batch reactor, we can calculate the time required in order to achieve the desired conversion, right? Which comes out to be 0.09 hours or 5.4 minutes. Okay, which means in order to achieve the 90% conversion, if we are using batch reactor, then we will require 5.4 minutes or 0.09 hours of reaction time in order to achieve the desired conversion of 90%. I hope you understood, right? Now, in order to design the volume of the batch reactor, the question was how large volume of batch reactor do we require, right? Then I have made you understand the actual method to design the volume of the batch reactor, right? If you want to understand, if you want to recall, I request you to please watch the previous lectures, right? So by using that actual method to design the volume of the batch reactor, right, where we have put all the values and we have solved the we have tried to calculate the design volume requirements, which comes out to be 1.35 cubic decimeter volume of the batch reactor we require, right? Which means by keeping all the operating parameters to be constant, if we carry out the reaction in the batch reactor and the reaction follows second order reaction kinetics with the given rate law minus RA is equal to KCS square, then we required 1.35 cubic decimeter volume of the batch reactor and 0.09 hours or 5.4 minutes of reaction time in order to achieve the desired conversion of 90%, right? I hope you understood. Okay, now let's say, what if instead of CSTR, PFR or batch reactors, now what if I use packed bed reactor, right? Then how large volume of packed bed reactor do we require? What will be the reaction time? How much weight of the catalyst do we require in order to achieve the desired conversion of 90%, right? So let's understand that, right? So let's say again, we are keeping all the operating parameters to be constant. Now we are carrying the reaction in the packed bed reactor. The reaction follows second order reaction kinetics with the given rate law minus RA is equal to KCS square, right? So by understanding the performance equation of packed bed reactor, we have calculated the weight of the catalyst which is required in order to achieve the desired conversion, right? So by utilizing the performance equation of packed bed reactor, we have calculated the weight of catalyst which is required in order to achieve the desired conversion of 90%, right? Which comes out to be 1.35 kg weight of catalyst we will required in order to achieve the desired conversion of 90%, right? I hope you understood. Okay, now again we are designing the volume of the packed bed reactor, right? So I have also make you understand the actual method to design the volume of the packed bed reactor. If you want to recall, I request you to please watch the previous lectures, right? So by using that actual method to design the volume of the packed bed reactor, we have calculated the required volume, which comes out to be 2 cubic decimeter volume we will require, and by using the fundamental concept of the space-time, we have calculated the reaction time, which comes out to be 0.1333 hours, right? Okay, which means 8 minutes of reaction time we will require in order to achieve the desired conversion of 90%, right? Which means by giving all the operating parameters to be constant, now we are carrying the reaction in the packed reactor, and the reaction follows second order reaction kinetics. Then we required 1.35 kg weight of the catalyst. We required 2 cubic decimeter volume of the packed reactor and 0.1333 hours or 8 minutes of reaction time in order to achieve the desired conversion of 90%, right? I hope you understood. Okay, now let's say we will make the engineering conclusion, right? We'll understand the engineering conclusion. Okay, now let's say we will try to compare the different reactor models. Okay, we'll try to compare the different reactor models with the required volume and the reaction time, and we'll try to make the engineering conclusion which reactor we should prefer in order to carry out the reaction, right? So let's say if we compare CSTR with the PFR, then by comparing the reactor models with the volume and the reaction time, we can see that if, right, so let's say for all these reactor models, right, for all these different reactor models, we have kept all the operating parameters to be constant. We have kept same reaction. The reaction follows, and the reaction follows second order reaction kinetics with the given rate law minus RA is equal to Kc square, right? Now let's say if we are carrying that reaction by using the different reactor models, then if we compare CSTR with the PFR, then let's say we can observe that we required larger volume of CSTR as compared to the PFR, which is 1.35 cubic decimeter, right? Which means if we use CSTR as the reactor model, then we require 13.5 cubic decimeter reactor volume, and if we use PFR as the reactor model, then we require 1.35 cubic decimeter reactor volume, right? And the reaction time is here 0.9 hours or 54 minutes of reaction time which is required, and here 5.4 minutes of reaction time is required in order to achieve the desired conversion of 90%, right? So let's say in the comparison of CSTR versus PFR, CSTR requires higher reactor volume and higher reaction time, right? So again, I repeat, the CSTR requires larger reactor volume and the larger reaction time as compared with the PFR, and PFR requires lower reactor volume and smaller reaction time in order to achieve the same desired conversion of 90%, right? So in the comparison of CSTR versus PFR, I would select PFR as the reactor model in order to carry out the reaction, right? Because if I select PFR as the reactor model, then I require a very small reactor volume, and I also require very lesser reaction time of 5.4 minutes in order to achieve the same desired conversion of 90%, right? I hope you have understood. Now let's say in the second comparison, what if I compare between PFR and the batch reactor, right? So now it is interesting. So we can say that if we make the comparison between PFR and the batch reactors, we can see that we require same reactor volumes of PFR and the batch reactors, and which is 1.35 cubic decimeter and 1.35 cubic decimeter, right? Okay, and we also required same reaction time of 0.09 hours or 0.09 hours, right? Which means 5.4 minutes of reaction time in both the case PFR and the batch reactor, right? So why it is so, right? We need to understand that. So in the previous lecture, I have made you understand that if the batch reactor operates as the time-based PFR, right? If you want to recall, I request you to please watch the previous lectures, right? Here the batch reactor is operated as a time-based PFR, which means at the starting of the reaction, when the conversion is 0, where we have fed all the feed mixer to the batch reactor, right? So at the starting of the reaction, we have the highest concentration of the reactant present, right? So highest the concentration of the reactant presence, we have the direct proportionality sign with the reaction rate. So higher the rates of the reactions, right? Due to which will require a smaller reactor volume and smaller reaction time in order to achieve the desired conversion, right? Okay. And with the progress of the reaction, slowly and gradually the concentration of the reactants will get consumed and will get converted into the new product, right? So with the progress of the reaction, slowly and gradually the concentration of the reactants will decrease, right? Which, okay, along the progress of the reaction, right? So same way in the case of PFR, as the inlet of the PFR, where we are feeding the feed mixer to the reactor via inlet stream, right? The inlet portion of the PFR, we have the presence of highest concentration of the reactants, right? So due to the higher concentration present at the inlet of the PFR, we have the direct proportional sign of the concentration with the reaction rate. We will have the higher rates of the reaction. Along the length and volume of the PFR, the concentration of the reactants slowly and gradually will decrease, right? Due to which the rate of the reaction will also decrease, slowly and gradually will decrease, right? At the outlet stream of the PFR, where the concentration of the reactants is minimal presence or there is no concentration present, which means in the case of batch reactor, at the completion of the reactions where we have minimal presence of unreacted reactants or there are no reactant presence, right? And in the case of PFR, at the outlet stream of the PFR, same, there is minimal presence of unreacted reactants or there are chances that all the reactants are consumed, right? So which means due to the lowering in the concentration, which results into the lowering in rates of the reaction due to the direct proportionality sign of reaction rate with the concentration, right? Okay, so same way, so the batch reactor will behave as a time-based PFR, right? So due to those reasons, we have obtained the same design volume of PFR in the batch reactor, which is 1.35 cubic decimeter volume, okay? And same reaction time of 0.09 hours in the case of PFR in the batch reactor, right? Which means 5.4 minutes of reaction time, which is required, right? So, okay, I hope you have understood, right? So in order to achieve the same design conversion, we can use either of the PFR and the batch reactor, right? But if we use batch reactor, then we'll have the higher operational cost and the higher maintenance cost, right? Which will be very costly, right? So in order to, and which will also result in the which will also affect the productivity of the desired chemicals, right? So, and the PFR is a continuous flow reactor, which means continuously we are feed mixture to the reactor. In the reaction environment of the PFR, continuously the reaction will take place, the product will form, and product will exit, and continuously the product will exit through the outlet stream of the PFR, right? Which means we can increase the productivity, okay, of the chemicals by using the PFR, right? And if we select the batch reactor, then we'll have the higher operational cost and the higher maintenance cost, right? So in order to avoid those increase in the operational cost and the maintenance cost, we'll try to select PFR as a reactor model in comparison of the PFR with the batch reactor, right? We'll prefer PFR as the reactor model, okay? I hope you have understood, okay? So here we have completed the second comparison, right? Now the third comparison is between the CSTR, PFR and batch reactors with PBR, right? Okay, so let's say if I select packed bed reactor, then we require the packed bed reactor in which we require the entire tubular space of the packed bed reactor is filled with the solid catalyst, right? Or the solid inert materials, okay? And or let's say if we are using the solid catalyst as the packing material, right? And on which the solid fluid interactions will take place and the reaction will take place, right? Then we require 1.35 kg weight of the solid catalyst, okay? And by using the packed bed reactor, we required 2 cubic decimeter volume and 8 minutes of reaction time, right? In comparison with the PFR and the batch reactors, we required 8 minutes of reaction time, and here we required 5.4 minutes of reaction time, okay? In the case of PFR and batch reactors, we required 5.4 minutes of reaction time, and if we select packed bed reactor, then we required 8 minutes of reaction time in order to achieve the same design conversion of 90%, right? I hope you understood, okay? Now, let's say in terms of volume, let's say in the case of packed bed reactor, we required larger reactor volume of 2 cubic decimeter, right? As compared to the PFR and batch reactors, where we required 1.35 cubic decimeter of reactor volume, right? I hope you understood, right? So if we select from the PFR and batch reactors, then we required lesser reactor volume as compared to the packed bed reactor, right? I hope you understood, okay? So let's say now we'll make the overall conclusion, okay? See, the overall conclusion is based upon the data, okay? The data which we have calculated, right? Okay, but in reality, the decision of selecting the reactor model will be based upon the different real industrial applications, right? Okay, if we want to have the good chemical purity, if we want to synthesize with the good chemical purity, then we may select batch reactor, right? Okay, as the reactor model. Okay, or we can also select the packed reactor. Okay, the selection in the real industry is the selection of the reactor models will be based upon many engineering parameters, right? Let's say the viscosity of the fluids, the solid, the bulk density, the pressure drop, the purity of the chemicals, the productivity, manufacturing, the synthesis of chemicals, right? The viscosities of the reactants or the product streams, okay, and many other heat transfer, mass transfers, right? The diffusivity, okay. So based upon all the industrial, based upon all the real engineering different parameters, the decision of the reactors will be made. But in today's lecture, in order to make you understand in a very simplified way, let's say by observing these entire engineering conclusion, let's say engineering calculations, let's say from the entire, from all these different reactor models, we will try to select PFR as the reactor model, right? The reason behind is we'll try to select the PFR as the reactor model, right? The reason behind is the PFR is a continuous flow reactors, which means we'll have the feeding of the feed mixer continuously by endless stream of the reactor. In the reaction environment, continuously the reaction will take place and products will be formed. The product will exit through the outlet stream of the PFR continuously, right? Which means we can also increase the productivity, we can also increase the manufacturing of the chemicals, synthesis of the chemicals, right? Okay, and which is cost effective, okay, as compared to all the reactor models, right? Because we also require lesser reactor volume as compared to the CSTR and packed bed reactors, right? Okay, and we also required lesser reaction time of 5.4 minutes as compared to the packed bed reactor, where we required 8 minutes of reaction time, and as compared to the CSTR, where we required 54 minutes of the reaction time, right? If okay, so due to those reasons, we can prefer the PFR as the reactor model, where we required lesser reactor volume of 1.35 cubic decimeter and lesser reaction time of 5.4 minutes in order to achieve the same design conversion of 90%, right? I hope you have understood. Okay, so so here we have understood the engineering conclusion for the industrial reactor design, where the reaction follows second order reaction kinetics with the given rate law minus RA is equal to KC square, right? I hope you have understood. So I request you to please make all the notes. Okay, I hope you have made the notes, right? Now let's say we will dwell more deeper into the fundamental understanding of the reaction kinetics, right? We'll dwell now more deeper into the fundamental understanding of the second order reaction kinetics, right? Where the reaction follows second order reaction kinetics with the given rate law minus RA is equal to KCA square, right? We'll try to come, we have, so here we have the fundamental cases, right? Where we'll try to understand how so here we'll try to understand the kinetics of the second orders, right? We'll try to understand how the changing rate of the reactions, the rate constants, the concentration will have effect in the reactor volumes, the space time, and the amount of weight of the catalyst requirements, right? So let's get started and let's understand. It will be more interesting, right? So the first case where, let's say the first case in which, let's say I'm making the concentration to be constant, right? Initial concentration to be constant. Okay, now understand that we are keeping the initial constant. Now this, let's say we are trying to understand the second order reaction kinetics, right? Where the with the given rate law minus RA is equal to KCA square. Okay, the reaction rate is indirectly proportional, with the constant rate constant, okay, and concentration C square. Okay, which means if we increase the rate constant K, then due to the direct proportionality sign with the reaction rate, if we increase the rate constant K, then the reaction rate will also increase. Okay, I hope you have understood. Now let's say here we also see that we have the direct proportionality sign of reaction rate with the concentration, right? Which means if we increase the concentration, due to the direct proportionality sign with the reaction rate, then if we increase the concentration, which will result into the increase in the rates of the reaction. I hope up to here you have understood, right? So similar way, due to the direct proportionality sign of the reaction rate with the rate constant K and the concentration, which means if we decrease the rate constant, and then the reaction rate will also get decreased. Okay, and similarly, if we decrease the concentration of the reactants due to the direct proportionality sign with the reaction rate, the rates of the reaction will also decrease, right? I hope you understood up to this part, right? Okay, so let's say now we'll understand each and individual case individually, right? The first case where I have kept the concentration, initial concentration to be constant. Okay, now what if I increase the rate constant? Okay, so how will it affect on the reaction rate? How will it affect on the volumes of the reactors? How will it affect on the space time, the reaction time of the different reactor models? And how will it affect on the requirements of the weight of the catalyst, right? We'll understand that. Okay, so let's say in the first case, I'm making the initial concentration of the reactants present in the reaction environment of the reactor to be constant. Now, what if I increase the rate constant value, right? So by increasing the rate constant value, we can say that by understanding the rate law, where the minus RA, with the given rate law minus RA is equal to KCS square, right? So here we have kept the concentration to be constant. Okay, now we can compare the reaction rate with the rate constant, right? So in the first case, we are increasing the rate constant. So by increasing the rate constant due to the direct proportionality sign with the reaction rate, the rates of the reaction will also increase, right? Which means by increasing the rate constant, the reaction rate will increase, which means the speed of the reaction will increase, right? So due to the increase in the speed of the reaction, which means we will require smaller reactor volume in order to achieve the same design conversion. Okay, due to which the requirements of the design volumes, okay, due to which the required volumes of the reactor will decrease. I hope up to here you understood, right? So the required volumes of the CSTR, PFR, packed bed reactor volume will decrease, right? I hope you understood up to this. Okay, why? Because the rates of the reaction has increased, which means the speed of the reaction has increased, right? Which result into the requirements of the smaller reactor volumes, and will due to the increase in the speed of the reaction, which means the faster rates, the faster speed will achieve the desired conversion, right? Which will result into the decrease in the reaction time. Okay, so due to which the reaction time of the batch reactors as well as the different reactor models will also decrease, right? I hope up to here you have understood, right? Okay, so here the K represent the rate constant, the C naught represent the initial concentration of the reactants present in the reaction environment of the reactor, minus RA represent the rates of the reaction, nu naught represent the volumetric flow rate, rho B represent the bulk density, and we have the CSTR volume, we have the PFR volume, we have the batch reaction time, we have the packed bed reactor weight of the catalyst requirement, and packed bed reactor volume. Okay, I hope up to here you have understood, right? So in all the cases, I'm making the volumetric flow rate to be constant, okay, and the bulk density also constant, right? So okay, I hope up to here you have understood, right? Okay, so now we have understood the first case, right? Now we'll try to understand these phenomena. Okay, now we'll try to understand the engineering interpretation for the first case, right? Now we'll observe this phenomena when, let's say, we'll observe this phenomena when there is an increase in the temperature of the reaction environment. Okay, we are keeping the concentration of the reactants to be constant. Okay, and we'll observe this type of phenomena when there is an increase in the temperature of the reaction environment of the reactor. So due to the increase in the temperature of the reaction environment of the reactor, which will result into the increase in the rate constant K, right? So due to the increase in the temperature will result into the increase in the rate constant K. If the K is increasing due to the direct proportionality sign, the reaction rate will also increase, right? Which means the speed of the reaction will increase, right? due to which will require the speed of the reaction has increased, which means we require now smaller volumes of the reactors in order to achieve the desired conversion. We require lesser reaction time in order to achieve the desired conversion, right? And we will require lower weights of the catalyst in order to achieve the desired conversion, right? So due to those reasons, the requirements of the volume of CSTR will decrease, the PFR required volume will decrease, the time requirement in order to achieve the desired conversion will also decrease, right? The weight of the catalyst will also decrease, okay, and the volume of the packed reactor requirements will also decrease due to the increase in the temperature of the reaction environment, which result into the increase in the rate constant K, which result into the increase in the reaction rate, which means the speed of the reaction has increased, right, which resulted into the desired volume requirements to be lower, okay, which result into the decrease in the reaction time and the decrease in the amount of weight of the catalyst which required in order to achieve the desired conversion of any desired conversion, right? I hope you have understood. So here we have completed the first case, right? I hope you have understood. Now we'll understand the second case, right? Now in the second case, again I'm making the concentration to be constant, okay? Now let's say, what if the rate constant is decreased, right? Again, we are making the concentration of the initial CA0 represent the concentration, right? So we are keeping the initial concentration to be constant. Now what if we decrease the rate constant, right? So by decreasing the rate constant, the rates of the reaction will also decrease, right, due to the direct proportional design of the reaction rate with the rate constant, right? Okay, which means the speed of the due to the decrease in the rates of the reaction, which means the speed of the reaction has decreased, right? Now due to the decrease in the speed of the reaction, now in order to achieve the same desired conversion, we will require larger reactor volumes, right? So due to those reasons, the design volumes of the different reactor models will increase, right? Which means we require larger reactor volume in order to achieve the same desired conversion. And due to the decrease in the speed of the reaction, now will require larger reaction time in order to achieve the same desired conversion, right? I hope you have understood. And which will also result into the increase in the weight of the catalyst requirements, right? Due to the decrease in the reaction rate, due to the decrease in the speed of reaction, right, which resulted into the requirements of larger weight of the catalyst in order to achieve the same desired conversion, right? I hope you have understood. Now we'll understand the engineering interpretation for the second case, right? So this type of phenomena will observe when there is a decrease in the temperature of the reaction environment, right, where the concentration of the reactants is kept constant. We'll observe this type of phenomena when there is a decrease in the temperature of the reaction environment, right? So due to the decrease in the temperature of the reaction environment, which resulted into the decrease in the rate constant K, right? Due to the direct proportionality design of the reaction rate constant K with the reaction rate, the reaction rate will also decrease. Due to the decrease in the rate constant, the reaction rate, the rates of the reaction will also decrease, right? The reaction rate decreases, which means the speed of the reaction will also decrease, right? So due to the decrease in the speed of the reaction will result into the requirements of larger reactor volume and the larger reaction time and larger weight of the catalyst in order to achieve the same desired conversion. Okay, I hope you have understood, right? So here we have completed the understanding of the second case. Now we'll understand the third case, right? Now let's say, what if I make the rate constant to be constant, right? Okay, now what if I make the rate constant to be constant? And what if I increase the concentration of the reactants, right? Okay, now it is very interesting. So we are making the rate constant to be constant now, and now we are increasing the initial concentration of the reactants present in the reaction environment of the reactor. Okay, so we are increasing the concentration of the reactants into the reaction environment of the reactor. So how does this affect, how will it affect on the reaction rate and the required volumes of the reactors? How does this affect on the weight of the catalyst requirement, on the reaction time? We'll understand that. So let's understand that. So in the third case, we are keeping the rate constant to be constant. Now we are increasing the initial concentration of the reactants, right? So, okay, so by increasing the concentration of the reactants, due to which, see here in the rate law, where the reaction rate is in direct proportional with the concentration, right? Which means if we increase the concentration of the reactants little bit, if we increase concentration of the air concentration present in the reaction environment with the little bit higher amount, right, which will result, and here you can see we have the square of the concentration, right, which will result into the higher increase in the rates of the reaction, right, which means a very little increase in the concentration will result into the multiple increase in the rates of the reactions, right? So due to which we can observe that there is a strong increase in the rates of the reaction, right, which means we will observe a strong increase in the speed of the reaction, right, which means now the speed of the reaction is very fast, right? So due to the increase in the speed of the reaction, now we will require a very smaller reactor volume, right? So requirements of the design volume of the reactors will decrease very strongly, right? Okay, will decrease very strongly. Okay, I hope you can observe. Okay, and due to the fast speed of the reactions, we require a smaller reactor volume, and will also result into the smaller reaction time, or the time of the reaction will strongly decrease, right? Okay, and will also result into the larger decrease in the weight of the catalyst, right, which means we'll require now smaller weight of the catalyst in order to achieve the same desired volume. Okay, I hope up to here you have understood, right? Now we'll understand the engineering interpretation for the third case, right? So this type of phenomena will observe when the temperature of the reaction environment is kept constant, right? We are keeping the temperature of the reaction environment to be constant, which will result into the constant, right? And we are increasing the concentration of the reactants, right? So we are slightly increasing the concentration of the reactants into the reaction environment, right? So slight increase in the concentration of the reaction environment, slight increase in the concentration of the reactants into the reaction environment, which result into the multiple increase in the speed of the reaction, right? Okay, so we'll observe the strongly increase in the reaction rate, which result into the strong increase in the speed of the reaction, right? Due to which will require a smaller reactor volume. So we'll observe the strongly decrease in the required volumes of the reactors, and we'll also observe that due to the smaller reaction volume, okay, due to the increase in the speed of the reaction, now we required lesser reaction time in order to achieve the same desired conversion, right? And we'll also observe that the weight of the catalyst is also strongly decreased, right? I hope up to here you have understood, right? Okay, so here we have completed the third case, right? I request you to please make the notes. Okay, I hope you make the notes, right, up to here. Now let's say we'll understand the fourth case. Okay, in the fourth case, again we are keeping the rate constant to be constant. Now what if we decrease the concentration of the reactants in the reaction environment of the reactor, right? So we are slightly decreasing the concentration of the reactants into the reactor, right? So due to the direct proportionality sign, if we decrease the initial concentration of the reactants into the reaction environment of the reactor, and here we have the squaring of the concentration, which means the concentration of the reactants will decrease, right? And we have the direct proportionality sign of the concentration with the reaction rate. So due to the slight decrease in the concentration will result into a multiple times decrease in the rates of the reaction, right? A multiple times decrease in the rates of the reactions, right? Okay, due to the slight decrease in the concentration, which result into the multiple times decrease in the reaction rate, which means the speed of the reaction has decreased very strongly due to slightly decrease in the concentration, right? I hope you understood. Okay, so due to this effect, which will result into the requirements of larger reactor volumes, right? So due to the strongly decrease in the reaction rate, which means the speed of the reaction is strongly decreased, right? Now, in order to achieve the same desired conversion, we will require larger reactor volumes, right? So there we'll find that the requirements we'll find that the desired volumes of the different reactor models has strongly increased. Okay, and due to the decrease in the strongly decrease in the rates of the reaction, which means the speed of the reaction has strongly decreased, right? Which means now we'll require larger reaction time in order to achieve the same desired conversion, right? I hope you understood. Okay, so the reaction time will also increase strongly. Now in the case of packed bed reactor, due to the same reason of the strongly decrease in the rates of the reaction, the weight of the catalyst requirement will strongly increase, right? Because we need to achieve the same desired conversion, right? So due to those reasons, the weight of the catalyst will strongly increase and volume of the reactor will also strongly increase. Okay, I hope you understood, right? Now we'll understand the engineering interpretation for the fourth case, right? So this type of phenomena will observe when the temperature of the reaction environment is kept constant, right? So by keeping the temperature of the reaction environment to be constant, which means the weight constant will remain constant. Okay, now simultaneously we are also slightly decreasing the concentration of the reactants present in the reaction environment, right? So due to the slight decrease in the concentration of the reactants present in the reaction environment of the reactor, which will result into the multiple times decrease in the rates of the reaction due to the direct proportionality sign of reaction rate with the concentration, right? So if there is a slight decrease in the concentration of the reactants, here we can see the rates of the reaction is in multiple times with the concentration, right? So due to the slight decrease in the concentration of the reactants will result into the strongly decrease in the reaction rate, right? Which means we'll see that the speed of the reaction has strongly decreased, right? So due to which, in order to achieve the same desired volume, now we will require very larger reactor volumes in order to achieve the same desired volume. We will require larger reaction time in order to achieve the same desired conversion. We will require larger weight of the catalyst in order to achieve the same desired conversion, right? So due to those reasons, the requirements of the reactor volume will increase, the space time will also increase, and the weight of the catalyst will also increase strongly, right, in order to achieve the same desired conversion, right? I hope you understood. So here we have completed the fourth case, right? Now we'll understand the fifth case. In the fifth case, let's say, now what if simultaneously I increase the rate constant K, and simultaneously I'm increasing the concentration of the reactants present in the reaction environment of the reactor, right? So due to this simultaneously increase in both the rate constant K and the initial concentration of the reactants, how will it affect on the reaction rate and the other reactor parameters, like the desired volume of the reactors, the space time of the reactors, the desired conversion, and the desired weight of the catalyst, right? So we'll understand that. Okay, so let's say in the fifth case, we are simultaneously increasing both the rate constant also we are increasing simultaneously, and simultaneously we are also increasing the concentration, right? So due to this simultaneously increase in both rate constant and the concentration, right, it has the reaction follows second order reaction kinetics, where we can see the reaction rate is in direct proportionality with the rate constant K and the concentration, right? Now we are increasing simultaneously, the rates of the rate constant is increasing and the initial concentration is increased, right? So initial concentration is increased, which means the concentration is the square of the square, right? Due to which we'll observe that we have the direct proportionality sign with the reaction rate. Okay, so due to the simultaneously increase in rate constant K and the concentration, we'll observe that the reaction rate will increase very large. Okay, the reaction rate will increase very large. Okay, I hope up to here you have understood, right? Which means the speed of the reaction is now becomes very large, which means in very microseconds, in few seconds, in milliseconds, the reaction will tends to completion and will achieve the desired conversion, right? Due to the speed of the increase, the speed of the reaction has increased very large, right? So which result into the largely decrease in the volumes of the reactor. Okay, which means now due to the increase in the due to the very large increase in the reaction rate, which means the speed of the reaction has increased very largely, right? Which result into the very large decrease in the requirements of the volumes of the reactor models. Okay, and the reaction time will also decrease very largely. Okay, and the requirements of the weight of the catalyst will also decrease very large. Okay, I hope you understood up to here, right? Okay, so let's say we'll understand the engineering interpretation for the fifth case. Okay, so now this phenomena is observed when there is an increase in the temperature of the reaction environment. Due to the increase in the temperature of the reaction environment, the rate constant will also increase, right? And simultaneously the initial concentration of the reactants is also increased. So due to the simultaneous effect of increasing both the rate constant K and initial concentration C0, which will result into the multiple times very large increase in the reaction rate, right? Which means the speed of the reaction has increased very largely, which will result into the requirements of very, due to which will result into the very strongly decrease in the requirements of the volumes of the reactor, very strong decrease in the requirements of reaction time, and strongly decrease in the requirements of the weight of the catalyst, right? I hope you understood, and we'll achieve the same desired conversion, right? I hope you have understood. So here we have understood the fifth case, right? Now we'll understand the sixth case. Now what if simultaneously both the rate constant K and initial concentration is decreased simultaneously, right? So how does this affect on the reaction rate and the desired volumes of the different reactor models, on the requirements of the weight of the catalyst, on the reaction time? We'll understand that, right? So in the sixth case, we can see that we have the simultaneous decrease in the rate constant K and the initial concentration, right? So due to the simultaneous decrease in both rate constant and initial concentration, right, we due to the direct proportional design with the reaction rate, we can say that due to the simultaneously decrease in both the rate constant and the concentration will result into the multiple times decrease in the reaction rate, right? Which means we'll see that the rate of the reaction will very large decrease, very strongly decrease, right? Which means the speed of the reaction has decreased very strongly. Now in order to achieve the same desired volume, in order to achieve the same desired conversion, now will require very large reactor volumes, will require very large reaction time, will require very large weight of the catalyst in order to achieve the same desired conversion, right? I hope up to here you have increased, right? You have understood, right? So you can see the requirements of the design volumes of the different reactor models has increased very largely. The space time of the reactors has also increased very largely. The requirements of the weight of the catalyst has also increased very largely, right? I hope up to here you have understood. Now we'll understand the engineering interpretation for the sixth case. So this type of phenomena will observe when there is a decrease in the temperature of the reaction environment of the reactor, right? So due to the decrease in the temperature of the reaction environment of the reactor, the rate constant will also decrease, okay, due to V, okay, and simultaneously the concentration is also decreased, right? So due to this simultaneously effect of decreasing temperature will affect into the decrease in the reaction rate, and during the progress of the reaction the concentration is also decreased, right, simultaneously, so which will result into the very large decrease in the rates of the reaction due to the direct proportional design of reaction rate with the rate constant and the concentration, right? Which means we'll observe that the speed of the reaction has decreased very largely, right, which will result into the very large increase, which will result into the requirements of very large reactor volumes, will require very large reaction time, will require very larger weight of the catalyst in order to achieve the same desired conversion, right? I hope you understood. So here we have completed the sixth case. Now we'll understand the seventh case, right? In the seventh case, let's say, now what if the rate constant is increased and simultaneously, now what if the concentration is decreased, right? So due to this simultaneously an opposite effect of increasing rate constant K and decreasing initial concentration, how does this will affect the rates of the reaction, and how does this will affect on the design volumes of the different reactor models, the reaction time of the different reactor models, and the weights of the catalyst requirements, right? We'll understand that, right? So let's understand that. So in the seventh case, we are understanding that we have the two opposite effect taking place simultaneously, which is where simultaneously where the rate constant is increased and simultaneously the initial concentration is decreased, right? So due to this simultaneously an opposite effect of increasing rate constant K and decreasing initial concentration, why concentration, right, will result into the constant rate of the reaction, or there may be possibilities of slightly increase in the reaction rate. Okay, I hope up to here you have understood, right? Okay, and due to this constant rates of the reaction, there are possibilities that the required volumes of the different reactor models may remain constant. Okay, or there may be possibility that due to the increase in the rates of slightly increase in the rates of the reaction, which means there is a slight increase in the speed of the reaction, right, due to which we may also observe that maybe there may be a slight decrease in the required volumes of the CSTR, PFR, batch reactors, weight of the catalyst will also decrease slightly, or the volumes of the PBR reactor will also decrease slightly, right? I hope up to here you have understood. Okay, now we'll understand the engineering interpretation for the seventh case. So in the seventh case, you can see that there is an simultaneously effect taking place and two opposite effect taking place together, right? In the first case, in the first part, where we can see there is an increase in the rate constant, right, which is the result of increase in the temperature of the reaction environment. If the temperature of the reaction environment is increased, we'll observe the increase in the rate constant K. Okay, and simultaneously the consumption of concentration is concentration of the reactants is also increased, right, due to which the concentration of the reactants will decrease, right? So due to these two opposite effects taking place simultaneously, right, which will nullify the rates, right, which means in the one part the rate constant is increased and in the another part the concentration is decreased, right? So due to this simultaneous effect of increasing rate constant and the decreasing of the concentration, which will nullify two effects, right, due to which the rate constant, due to which the reaction rate will remain constant, or there might be a possibility that the increase in the rate constant will have effect into an increase in slightly increase in the rates of the reaction due to the direct proportional sign of reaction rate with the reaction rate with the rate constant, right? So due to those reasons, the reaction rate will remain constant, or we may observe that slightly increase in the rates of the reaction, right? So due to these reasons, the volume of the different reactor models will remain constant due to the rates of the reaction is constant, right? Or there may be also other possibilities due to a slightly increase in the rates of the reaction, which means there is a slight increase in the speed of the reaction, right? Due to which will result into the slight decrease in the requirements of the reactor volume, okay? And the reaction time will also decrease slightly, and the weight of the requirements of the weight of the catalyst will also decrease slightly, and volume of the PBR reactor will also decrease slightly. I hope up to here you have understood, right? Now let's say here we have completed the seventh part, right, seventh case. Now we'll understand the eighth case, right? Now in the eighth case, now again there are two simultaneously opposite effect taking place. Now here in this case, the rate constant is decreased and simultaneously the concentration of the reactants is increased, right? Now how does this two opposite effect will affect the other reaction parameters, right? Okay, so let's understand that. So in the eighth case, you can see that the rate constant is decreased and simultaneously the concentration of the reactants is increased, right? So due to these two opposite effects taking place together, the rates of the reaction will get nullified or will may remain constant, or due to the decrease in the reaction rate constant, we may also observe that the rates of the reaction may also decrease slightly, right? Okay, and due to the constant rates of the reaction, we can observe that the volumes of the different reactor models will remain constant, or due to the slight decrease in the reaction rate, which means the speed of the reaction has decreased slightly, right, which will result into the slightly increase in the volume of the reactor, the reaction time, the weight of the catalyst, right? I hope up to here you understood, right? So now we'll understand the engineering interpretation for the eighth case, right? So this type of phenomena will observe when there is a decrease in the temperature of the reaction environment of the reactor. So due to the decrease in the temperature of the reaction environment of the reactor will result into the decrease in the rate constant K, right? And simultaneously the concentration of the reactant is increased, right? So due to these two opposite effects taking place together, the decrease in the rate constant K and increase in the initial concentration will nullify the change in reaction rate, due to which the rates of the reaction will remain constant. Or there might be other possibilities where due to the decrease in the rate constant value, the reaction rate may also decrease slightly, right? Will result into a constant requirements of the different reactor models, volume of the different reactor models may remain constant, or due to the slightly decrease in the reaction rate, the requirements of the different reactor models, the requirements of the reactor volume of different reactor models will increase slightly, okay, due to the slightly decrease in the rates of the reaction, right, will result into slightly increase in the requirements of the design volume of the different reactor models, okay, and the space time will also increase slightly, and the requirements of the weight of the catalyst will also increase slightly, right? I hope up to here understood it. So here we have understood, here we have completed the eighth case, right? So in order to conclude the entire lecture, in today's lecture I have concluded the industrial numerical example which follows second order reaction kinetics with the given rate law minus RA is equal to KCS square, where we have understood where we have made the engineering conclusion by using the different reactor models, the CSTR, PFR, packed bed reactors and batch reactors. We have tried to understand how we select the reactor models for the real industrial applications, right? Okay, followed by we have dwelled more deeper into the fundamental understanding of the second order reaction kinetics, where we have understood how the change in weight constant, the initial concentration of reactants and the rates of the reaction will affect the desired design volumes of the different reactor models, the requirements of the weight of the catalyst and the reaction time. Okay, we have understood in a very detailed manner, right? So I hope you have understood. So I request you to please make all the notes, right? And if you have any questions, feel free to comment below. I will try my best to reply to your comments, right? And in upcoming lectures, we will understand the different fundamental concepts of the chemical reaction engineering, right? So until then, stay focused, stay curious, and keep learning. Thank you for watching my video. Jai Hind.